Hello folks, and welcome back to another lesson. Today we're on to topic 7.2, and this deals with properties of exponential functions. Now we're going to start off by looking at this equation here. Y is equal to negative 2 times the absolute value of x minus 3 plus 1. How does it differ from its parent function? Well, what's the parent function here? It's y is equal to the absolute value of x. What does the negative 2 tell us? Well, the negative tells us that we're reflected across the x-axis, or flipped. The 2 tells us we're vertically stretched by 2. The minus 3 tells us we're going to be moving right 3. And the plus 1 tells us we're moved up 1. So we had each of these different things. We could reflect or we could flip, we could stretch or shrink, and we could move left or right. Today we're going to be looking at these same ideas, but this time with exponentials. So to start off, we're going to look at y is equal to 2 to the x, and then look at a couple of differences. Let's go ahead and pull out our graphing calculators to see what they look like. To start off, let's graph y is equal to 2 to the x and see what that looks like. So our first equation starts low and then starts moving up. Notice how at 0 it crosses 1 and then keeps going up. Okay, so that's our parent function here. Let's look at what happens when we change the sign out in front. So what happens when we graph y is equal to negative 1 times 2 to the x? Here we have our two equations. The new one is in red. And what do we see? We see that it goes down instead of up. Right? This has been flipped across the x-axis. So this equation here, the negative 1, flipped across the x-axis. And it left us with an equation looking something like this. Negative 8. So we got a function that looks roughly like this. Okay. What if we changed the values of a? So what if we made a larger? We said y is equal to 3 times 2 to the x. Or what if we made it smaller? We said y is equal to 1/2 times 2 to the x. We'll say this one will be red and this one will be, first one will be black, the second one will be red here. Let's graph those and see how they look in comparison. So here we have these two. We have y is equal to 3 times 2 to the x and y is equal to 1/2 times 2 to the x. So we're looking at red and black, seeing how they differ from the blue line. We start off with the blue line here. The red one looks like we've stretched it, we've pulled it up, so we vertically stretch it by 3. And the black line is smaller, it got vertically compressed. So what does that mean? It means our first function here, the one with 3 times 2 to the x, we vertically stretched by 3. And the second one here, the 1/2, we vertically compressed by 1/2. Meaning that our first equation looked like something like this. Um, So our equation looked like this, where our second equation was smaller. Okay, so there's two of the signs we're used to, or two of the changes. We flip across the x-axis by multiplying by a negative number out in front. We stretch and compress by multiplying by a number that's not the power number. What happens if we change the exponent? So now instead of writing 2 to the x, we're going to write 2 to the x plus 3 and 2 to the x minus 4. Let's see what those look like in our graphing calculators. Here we are. We have our equation set up with parentheses around our powers. I would always recommend anytime you're putting something in a power, anytime you're using this caret button here, you'd throw parentheses around whatever you want to put in here. So we're looking at the red and the black lines here, seeing how they differ. We have our original function. The red one, x plus 3, gets moved to the left, and the black equation here, x plus 4, x minus 4, gets moved to the right. So this one goes the opposite way of what we expect. The plus moves us to the left, the minus moves us to the right. So it seems like changing the exponent, adding or subtracting values, shifts us left and right. So x plus 3 shifts us left 3, and x minus 4 shifts us right 4. So we'll do the first one in black here. We're shifted left 3, and our second function is going to be in red here. We move to the right 4. Okay, and last but not least, what happens if we change the constant on the outside? So we have 2x, and then we're going to add 3, or we're going to subtract 3 to it. Let's throw those into our graphing calculator and see what shows up. Here we have these put in. Let's go ahead and look again. We're looking for red and black in comparison. So it looks like the red one got moved up by 3, and the black one here got moved down by 3. The easiest way to check this is to look at the asymptotes, or where it flattens out. The blue one flattens out at 0, the red one flattens out at positive 3, the black one flattens out at negative 3. So this tells us that the value outside, just like with our other functions, shifts us up and down. So plus 3 shifts us up 3, minus 3 shifts us down 3. So our first one, if we're graphing it, move up to here. We get something that looks like this. While subtracting 3 moves us down 3. In red, it's going to look something like this. And those are the four transformations that we know about. So let's combine them all together. Now we're talking families of exponential functions. The parent function for these will always be y is equal to b raised to the x. So whatever different power of x we have, or have different base, that will be our parent function. Now stretching, shrinking, and reflecting all had to do with our coefficient. So for these, we're looking at y is equal to a times b to the x. These are a stretch when our value of a is larger than 1. Doesn't matter whether it's positive or negative, it'll get stretched or increased when that value of a is greater than 1. It'll be shrunk, or it'll be smaller, if our value of a is less than 1. And of course, we'll reflect over the x-axis, or we'll flip when a is going to be a negative number, or a is less than 0. Now the parts for horizontally and translating, those came from the number inside of the exponent, so x raised to the x minus h, and our constant at the very end, plus k. So the number on the inside moved us horizontally. Translate horizontally by adding or subtracting to the exponent. Or by changing h. And translate vertically with k. Now let's look at do an example of how this function has changed from the parent function y is equal to 4 to the x. So we're looking at this and we have y is equal to negative 1/3 times 4 to the x minus 1 plus 5. So we have four different parts that are changed here. We have a negative, we have a 1/3, we have x minus 1, and we have plus 5. Let's start from the left and move our way right. To start off with, the negative is going to reflect us across the x-axis. Then the 1/3 is going to shrink us by 1/3, right? We're dealing with our coefficient here. So a vertical compress of 1/3. Okay. Then we have the minus 1, 4 to the x minus 1. We said numbers inside of the exponent shift us left or right, and to get flipped, just like normal left or right movement. So this is going to shift us right 1, and we're going to be shifted up 5 from the plus 5. Okay. Now you all try one. How does this function here, y is equal to negative 1 times 5 to the x plus 2, x plus 3 plus 2, how does that change from y is equal to 5 to the x? This one changes with a negative 1. It reflects across the x-axis. The plus 3 moves us left in this case because we flip our sign. So we're going to shift left 3. And the plus 2 is going to shift us up 2. So that's how we have changed this function. One more, now that we're dealing with our calculators, let's try making an example. Let's say you have these sets of values here. So medicine in your body follows an exponential decay. We're going to try to put each of these values in and find what the equation should be in the form y is equal to a times b to the x. So I will meet you with these values in our table. Remember, how do we get to our table? Well, tables are the same things as lists, so we're going to hit that Stat button here, and we're going to go into the Edit menu. Remember to delete out any values you have, but don't delete L1 and L2, just the values, and input your values in. So here we are with our values in. We converted our table with hours in L1 and our medicine in L2. Now to figure out what the exponent is for this, we're going to go back into our regression menu. So we're going to hit Stat, we're going to look under our Calc until we find something that looks exponential. So far nothing, but we get to 0 here, it says expreg, or exponential regression. Let's see if that's the one that works. Put this in, we make sure our X list is L1, right? That's what we set this up to be. Our Y list is L2. And let us calculate what this is. So it says y is equal to a times b to the x, which is exactly what we were looking for. So we have a times b to the x. It says a is 199.67 and b is 0.922 with a pretty accurate r squared. So let us write this down. Our equation would be y is equal to 199.67 times b was 0.922 to the x. So 199.67 times 0.922 raised to the x. All right, one last topic here. This is a fun one. We get to learn another weird mathematical thing here. What is E? You might have seen this button in your calculators before. Let's figure out what it is. Let's put in E and see what it comes out to be. So we see E above our divided button. If we put that in, it tells us E is roughly 2.71828. So E is going to be roughly 2.71828, and it comes from naturally repeating numbers. So E here is an irrational number. It keeps going on, so E is irrational. And it's called the natural base. Because we end up seeing it show up a fair amount in nature. One place that we will see E showing up is in compound interest. Remember, compound interest is just where interest is applied n amount of times over the course of your year. In general, if we have compounding interest and it's n times, so if it's 2 times, 3 times, 4 times over the year, our value looks like this. Our amount will be equal to whatever we put in, our price, times 1 plus our rate divided by the number of times we're going to put it in. And we're going to raise that to the n times time. Or A is equal to P times 1 plus R over N to the NT. So we're just taking up our rate, we're dividing it by N, and then we're raising it to the N times T. However, if we keep getting N closer and closer to infinity, if we keep trying to impound it more and more, we get to what we call compounding continuously, or it's compounding every millisecond, every microsecond. And when we do that, the equation changes to include E. So it becomes A is equal to P E to the RT. Or I like to think of it as A is equal to PERT. PE to the RT. Now let's go ahead and try to use these a couple of times. Let's say at age 8, your grandpa gave you $3,000 towards college. It's asking how much you would have at age 18. So from age 18 to 8, our time is going to be 10 years. If you made 4% interest, so our R is going to be 4%, compounded twice a year. Okay, so let's try compounding versus compounding continuously is the other part. 2 times a year versus compounding continuously. Okay, so compounding twice a year, we're going to use the formula A is equal to P times 1 plus R over N to the NT. Now what was the principal? The original amount we had was $3,000. and then that's going to be times 1 plus, our rate was 4%, so it'll be 0.04 divided by, we compounded twice a year. So it's not that we compound every half year, but we're doing it over a period of 2 times, raised to the 2 times our time. Right? So in this case, P is 3,000, R is 4%, N is going to be twice because we compound 2 times a year, and T is 10. We're going to throw that all into our calculator, and we're going to see that the amount of money we'd have from Grandma's account would be times 1 plus 0.04 divided by 2. We're going to raise that to the 2 times 10. We would have $4,457.84. What about if it was compounding continuously? Then we'd use the continuous compound formula. A is equal to PE to the RT. P would be the same thing. It's our principal amount, or $3,000. Our rate is still going to be the same. It's going to be 4%. And our time would be 10 years. So we throw that all in, we'd get A is equal to 3,000 times E raised to the 0.04 times 10, and see what that gives us for our calculators. So we get 3,000 e to the 0.04 times 10. You'd end up having a little bit extra money. If Grandma put this into a continuously compounding account, you would have $4,475.47. So a little bit of a difference, but imagine this over enough time or with enough money. Compounding continuously will tend to work out better. However, to be sure, let's check a second example. We're trying to decide whether to open a bank account or which bank account to open. We have $1,000 to invest. One offers 2.8% annually, but only pays you once a year. So there's no compounding, and the other pays 2.5 compounded continuously. So what are the two values here? Our two equations, the first one for the 1 time per year, we'd be using the formula that we're used to for compound interest, or for normal interest. We'd have A is equal to 1,000 times 1 plus 2%, or 1.028 raised to the t. But when we're compounding continuously, we would have A is equal to PE to the RT. So our principal was 1,000. We'd have E to the rate is 0.025% times time. We're looking to see if there's a certain number of years where it would make more sense to go with the lower interest rate, to go with the compounding continuously. So we're going to need to pull out our calculators and check these on that. Right, here we are. We're putting these into our calculator. So we have the first one implemented, the 2.8% compounded once a year. But for the compounding continuously, notice above the button that says ln, you should see an e to the x. If you press second e to the x, that should get you e with the power already there, which should be a 2.5% times time. Now we're going to need to adjust our window for this again, because we want to see what 1,000 is to start and how these continue to grow. So we're going to start off, we don't care about any negative years, but let's see, we might want to go out to 20 years. And we're going to start with $1,000 and keep going. Let's see if these change before we get to $10,000. Looks like my scale was a little wrong here. Looks like we were too ambitious on the amount of money we would make. So let's go back and let's change our Y maximum to be something a little bit more reasonable. Looks like we won't get past $3,000 here. And let's see which one of these makes more sense. Remember, our blue one is the compounding normally. The red one is compounding continuously. And it looks like the red one is always beneath the blue, so compounding continuously would not make sense in this case. Compounding continuously will not make sense. And that's all there is for this lesson.